Hello everyone and welcome to new discussion. It's a part 2 basically of discussion which we had about remote sensing applications in earthquake studies of this course. So, in the part 1 we have discussed how remote sensing can be applied in earthquake induced landslides and also how remote sensing data sets pre-earthquake, post-earthquake can be applied in earthquake induced liquefaction related studies. It is very much possible to map earthquake induced landslides and also liquefaction very accurately employing remote sensing data. Third and last application related with this earthquake which we are going to discuss is again employing remote sensing techniques, but this time in most of the examples I am going to show you the usage of thermal images. So far examples, in earlier examples what we have seen mainly visible or infrared bands or applications of those bands in earthquake related studies. Now we are going to discuss about how thermal remote sensing data can be employed in earthquake related studies. As you know that when earthquake occurs, generally they occurs along a fault line, but before that a lot of stresses are developed because of movement of these plates, crustal plates, like Indian plate is going below the Eurasian plate and so on and so forth. So, if we put this analogy, this is what we find that on right hand side, that if you bend a stick or a wood rod, then you keep bending and there will be a stage when it will break, and there exactly in case of earthquakes where what earthquake occurs. So, here the bending is going on, but there is no break, and here the bending has reached across the threshold and therefore the movement has occurred. Similarly, this is what you are seeing here. So, this the rupture will occur once it reach the threshold value or cross that threshold value. So, during that time there must be there must be some changes in temperature regime of the surface of the earth, and this is what we can further understand these changes in thermal regime by recalling our high school physics. We were taught that if you put a heavy coin on a sheet of ice like here, then after some time what you find that coin goes inside the ice, because the coin exerts pressure on the sheet of ice, and that pressure creates the little higher temperature that melts the water or melts the ice, and slowly coin moves inside the ice. So, this is what has happened. So, that means there is basically a simple interconversion of energy from pressure to temperature. Whether this thing also happens in case of earthquakes or related with earth, this is what we are going to see. There are some other reasons which can also bring higher temperatures near the surface during an earthquake event or before an earthquake event. So, two more processes which supports this increase in temperature, and one is this paired hole this positive hole pairs, and this can create during the reactivation or during the rupture, these positive holes pair, and they can come on the surface and can increase the temperature. Also there are lot of greenhouse gases which are entrapped in the pore spaces of rocks. So, just before the rupture, because of intense pressure or stresses, these gases can also come out and they can create a greenhouse effect, and that greenhouse effect means rise in temperature. So, all these things are contributing towards the rise of temperature. Now, it is sometimes very difficult to tell that which has shown its major effect on rise in temperature, but a combined effect which we can detect implying the remote sensing data, especially I am talking about the thermal remote sensing. Also, as you know that when these temperatures are measured on the ground, they are generally measured about 1.2 meter above the ground in a wooden ventilated box. And this has been the convention. Now we are having digital techniques. Because why I have mentioned this? Because this data we will be using to compare our land surface temperature maps derived from remote sensing data and air temperature. This we call as, this kind of measurement is called air temperature. Further, people have like organization like NASA, what they have done, they put a heavy pressure of 1500 ton press on a block of granite, and while doing this experiment, the thermal images were recorded. So, continuously we are recorded, and what it has been observed that before this rupture which you are seeing on the right side image, there were rise in temperature, and then of course the rupture has occurred. Whether such things are also happening in case of real earthquakes, that has to be also seen and understood. So, for that purpose we would like to what we look for thermal remote sensing data. There are few satellites. When we discussed different platforms and satellites and sensors, we discussed about those, but just to remind, one of the satellites which is having thermal channels and provides the data and cover a very large part of the earth or entire globe of the earth, because of relatively low spatial resolution, a swath width is very high, and that is the NOAA data, NOAA AVHRR. AVHRR is the sensor. And so what we ourselves are having this kind of setup or earth station which is capable of acquiring NOAA AVHRR data, and this earth station is operational since October 2002. Still it is continuing, and we are continuously acquiring in automatic fashion our remote sensing data from NOAA AVHRR series. These are the different components of this earth station. This is the receiver, and this is a simple PC based system, and say automatic system. So, whenever there are overpasses of NOAA series of satellites, the system will automatically acquire the data. Now, because of relatively having low spatial resolution, it covers a very large area, and as you can see that our antenna, that is our earth station, which is marked here as IITR SES, that is a satellite earth station, SES stands for. So, that can cover about 3000 kilometers radius area. That means anywhere in this circle in space, if satellite is there, our earth station is capable of acquiring data from that satellite. This is one of the examples of image which was acquired by our own satellite, which is or our own earth station of NOAA AVHRR data of 28 October 2002, and in a one this is not a mosaic, this is simple one swath image or one image, and which has covered almost 95 or 98% of Himalaya in just one go. So, that is the advantage, and this is multispectral sensor. That means there are two thermal channels also, visible channel, infrared channel, and two thermal channels. And another advantage, because having thermal channel, this sensor can also record images in night time, especially in three channels, one is infrared and two thermal channels. So, there are only few satellites which can give you the data of even night time. We will be also seeing those examples, how in earthquake studies, especially in pre-earthquake thermal anomaly detection, how we can employ daytime data, thermal data and night time data, and see what are the advantages and disadvantages. Now, what we see here, the first example I am going to take is again Bhuj earthquake of 26 January 2001. And this data is of course not from our satellite earth station. This data was acquired from NIO Goa, and though they were not recording regularly, so whatever the data which we got, the time series data, what we find that slowly the temperature was rising before the earthquake, as it reached to the maximum on 23rd January, and somehow we did not have the in between images, and on 27th January things started becoming normal. So, this was the first observation which we made using thermal remote sensing data. And later when we got our own data sets for the same dates and the identical processing, when we performed, we found that normally the temperature does not changes so frequently, so rapidly as has happened in the year 2001. As you can see here that hardly there are changes in these images. So, these are the same dates images, the only difference is the year. In this image they are all 2001, here corresponding dates, but the year is 2003. So, one observation. Second is about the, as I mentioned earlier, the air temperature. So, we also compared the air temperature data. This is 30 years weekly average data of a few meteorological stations which are shown in this map, and these stations in weekly average data all in the third week, the week in which the 2001 26 January earthquake occurred, third fourth week, and generally they were showing all low temperature. But in the year 2001 all these stations, few more which were not available between those 51 to 80, and they all have shown very high temperature for all these stations, and especially as you can see that the Bhuj station stopped working, got damaged due to earthquake event. So, as you can see that air temperature were also showing high values in that week, or in that week corresponding compared to the 30 years weekly average data. Employing other sensor, that is MODIS, another very popular sensor which is on two satellites Terra and Aqua. This MODIS sensor is also having two thermal channels almost identical to the NOAA AVHRR channels. That NOAA AVHRR channels about 1.1 kilometer spatial resolution, MODIS thermal channels are 1 kilometer resolution, and they too acquired data in daytime and night time. So, after our studies also the other people have also studied, and though they did not have the full time series data, the reason that MODIS was being tested during that time. The MODIS really declared operational only in 2002. So, whatever the tested images were there, as you can also observe that on 21st January 2001, 5 days before the earthquake, there were rise in temperature or land surface temperature, as you can see here. So, it basically matches with our interpretations, our analysis of thermal data of Bhuj earthquake. So, after getting encouragement from such kind of studies, especially on Bhuj, we started looking other earthquakes, not only a part of India, but other parts in the surrounding region, because as you know that our earth station can acquire data of not only India, but a large part of neighboring countries, including like Iran, though it is not directly neighbor country, but because of large capability of acquiring data, we could analyze many earthquakes of Iran and several earthquakes from different parts of the world. So far we have analyzed more than 28 earthquakes of different parts of the world, employing either data which was acquired by our own earth station or data acquired by other stations which have been shared with us. Now I am going to take example of BAM earthquake which occurred on 26 December 2003, magnitude was 6.6. The data was acquired by our own earth station, that is IITR CES. So now we are having full control on time series, and when we analyze the data, we are putting here only those images which are most relevant here. So what we remember that earthquake occurred on 26 December 2003, and temperature started rising from 22nd December onward, and on 24th December it has reached to the maximum, as you can see here. Of course, there were some clouds also were detected nonetheless, and things started becoming normal on 25th. They are going basically in the background. 26th is almost from temperature point of view is the same image as almost of 22nd December, but in between on that day the earthquake has occurred. So what we are seeing so far in these two examples, that there is a rise in temperature and the peak is reached before the earthquake occurs, and then earthquake occurred and things becomes normal. One important point which I want to mention, that we are not in prediction mode. We are still trying to understand this whole phenomena through different examples. Whether in each and every earthquakes of large magnitude such pre-earthquake anomalies are occurring. If they are occurring, then when, how early they are occurring and what happens just after the earthquake. So, this is all in hindsight. These are all post-mortem studies developing knowledge about pre-earthquake thermal anomaly, which are transient anomaly. And of course, later on, once a confidence is there, along with some other precursors related with earthquake, some forecast or prediction might be possible in long term or in future. But just based on one precursor like pre-earthquake thermal anomaly, nobody should think to forecast anything about this complex phenomena. So, all these results which I am showing here are all done after the earthquake has occurred. So, we knew where earthquake has occurred. This point you must note. Nonetheless, what you see a very important observation is that there is a systematic rise in temperature which reaches to the peak before the earthquake, 2 days, 3 days in different cases, and then things started becoming normal and earthquake occurs. So, this is one example. This was, if you notice that this was the daytime data from our own satellite earth station, and for the same earthquake we also employ the nighttime data. So, what we observed that on this 21st December, that means roughly about 5 days before the earthquake event, we saw a anomaly. The peak we saw in daytime, the anomaly was seen just 2 days before. In night time it was 5 days before. The reason is that in nighttime data you do not have the differential solar heating, and many times the meteorological differences, local meteorological disturbances are also generally less as compared to daytime. So, that is why it was very much possible to detect this pre-earthquake thermal anomaly 5 days before. Of course, in the post-earthquake analysis, that means in hindsight after the earthquake has occurred. So, but this definitely tells us that the nighttime data can be much more reliable than daytime data, especially in hilly regions. So, this is a not as rugged as like Himalaya, this part of Iran, but nonetheless it is also hilly region. Now, where we have detected, this is another point which should be noticed here, that the area which we have seen the anomaly, the same area had also co-seismic deformations. That means lot of changes in the ground has happened during that earthquake event of 26 December 2003. And these were mapped employing the SAR interferometry technique, again remote sensing technique. Of course, we personally did not do this analysis. This was done by Strumendo et al. In 2005. Later on, we also had our own data sets which we got from European Space Agency, and we analyzed. What we see that where we have noticed the pre-earthquake anomaly 2 days before or 5 days before in nighttime data, the same area got involved in co-seismic deformation, because otherwise some people might be thinking that this thermal anomaly is atmospheric phenomena rather than ground phenomena. So, this basically this tells us that this is not atmospheric phenomena, this is truly a land surface temperature phenomena or ground related phenomena. Now, when we analyze the data using this NVSAT data of the 26 December 2003 earthquake, this is the interferogram and this is what the ground deformation map. This is very ideal data was available, and as you can see that there were rise in some areas, the lower part, the red part has shown 30 centimeter up, and the green part has shown minus 20 centimeter down, and that is in the line of sight, because as you know that in radar data or radar remote sensing data, the data is not taken in nadir viewing, it is taken in oblique direction. So, it is the change in the line of sight, not directly vertical, but it can be converted and you can get more accurate values like these. So, you can know exactly which area got uplifted and which area has got subsided, induced by that earthquake event. We will take another example of pre-earthquake thermal anomalies which we have detected very clearly in the in our own data sets which we acquired from NOAA UHRR satellite. And this earthquake of which is known as Jarand earthquake of Iran occurred on 22nd February 2005. And again in time series data what we see here that there were build up of anomaly. It reached to the maximum on 21st Feb 2005, and unfortunately on 22nd, the day when earthquake has occurred, there were linear clouds. Things started becoming normal, but in between the earthquake has occurred. So, what we are seeing here in this example that about one day or 24 hours or maybe 36 hours before, they were the peak has reached to the maximum. But this is all in hindsight. If I am working in the real time for forecasting, then say on 21st I do not know how whether it will go further higher or I have reached the maximum, that I do not know. So, only when we are doing a postmortem, we are telling that the maximum has reached on 21st February. So, these are the things which have to be considered, and when to declare that maximum has reached if we are working in forecasting mode, which we are not working yet. That day is quite far. We have to develop that kind of understanding to employ this kind of technique towards the earthquake forecasting or prediction. But nonetheless, whatever is there, it is still allowing us to develop a knowledge or understanding about this phenomena. Now, in the Jarand earthquake also, that also witnessed the co-seismic deformation, and of course, this is by B. Parson, and this analysis was done. Same area was involved in co-seismic deformations. So, we are going to take another example of Bormades earthquake of Algeria of 21st May 2003. Of course, this is a different data set. Different in data sets means it is an average, daily average, one day average of this data set. This is the night time composite images of land surface temperature maps, and as you can see that there were rise in temperature in this part. This was very interesting, and then things became normal. Earthquakes have occurred. Earthquakes, I am using plural word because many earthquakes have occurred of after this 6.9 magnitude, 5.7, 5.5, 5.8, lot of earthquakes have occurred. If I see the blow up of that particular image where anomaly was maximum in this part, whereas epicenter was here. So, this brings another better understanding about this phenomena, that it is not necessary that where we are observing an epicenter, the same area will have the anomalous region or anomaly, because it basically depends on the fault which is responsible for that or those earthquakes or that particular event. So, in this case in Bormades earthquake of Algeria, the South Atlas fault, which is marked here as SAF, was responsible, and this can be explained here that epicenter is just a vertical projection of focus on surface. So, this epicenter is here, whereas the anomaly was seen all along this South Atlas fault. So, sometimes you may get offset of few kilometers or tens of even kilometers sometimes you may get, because it is not always necessary that where the epicenter is there you will get the anomaly. It depends all on the faults which are responsible for earthquake event or the movement along the fault which is occurring or the faults which are allowing the heat to escape, and therefore, the anomaly might be between epicenter and anomalous region there might be sometimes offset. Our interpretation was further supported by a study done by Poulinets et al. And they too use implying modest nighttime data, daytime data, as you can see here in the index, and that the peak was reached on 17th April, and then on 21st April the earthquake has occurred. So, by whether you employ VHRR data or MODIS data which provides the thermal channel, covers a large area, these data sets can be used to study such phenomena which are occurring before an earthquake event. Now, I will take one or two more examples where large offsets have been observed, and this says one example is from Chamoli earthquake. This example we have taken in case of earthquake induced landslides, the same earthquake, and when we got this data, of course this data was not from our own satellite earth station, because our earth station, if you recall, it started operating in October 2002. So, this earthquake has occurred in 99, but after a few years we got access to this data through again NIO Goa station, and what we here observe that the earthquake epicenter was here, as you can see a circle, but the anomaly was seen in form of a line, and that too quite maybe 60-70 kilometers south of epicenter, and that really perturbed us for some time, that how it is happening, why it is happening. And when we analyzed further, and we found this is the anomalous region, and we found that there are this Himalayan frontal thrust, and that along which Himalayan frontal thrust, this thermal line or thermal anomaly was observed. The earthquake and aftershocks were here. So, you can see about 60-70 kilometer south of this the anomaly was seen. And now, this is very important that why it is there, that they so much offset and the anomaly is appearing in a linear form. Linear form can be explained because the heat which could get escape all along this Himalayan frontal thrust. So, just hold for some time about this discussion, that why there is offset, why this thing. Let me take one more example, because when we saw this kind of phenomena, we could of course explain that why it has occurred, but when Nepal earthquake occurred, we wanted to check whether exactly same way in case of Nepal this has happened or not. And surprise and satisfaction to us was truly it has also happened in case of Nepal earthquake. As you can see of this Nepal earthquake, the first one of 25th April 2015, the anomaly appeared in the almost same way as in case of Chamoli earthquake. And you can see in the large view that see this all along this again Himalayan frontal thrust, the anomaly, the thermal anomaly appeared and again disappeared with the earthquake, or for some time it remained there, and not exactly in typical pre-earthquake thermal anomaly in other cases which we have seen. So, this why it is happening, why so big offset, this we could explain, which I am going to narrate here. As you see that this is the setup, is a schematic is that Himalayan frontal thrust is here. So, if earthquake is occurring here, the because this area is having very saturated water conditions, and if earthquake like Chamoli earthquake has occurred just a fag end of the winter month, and as you know the groundwater temperature is always constant. The temperature of surface water varies with the season, but the groundwater temperature remained same. So, what we think that because of this movement during that earthquake, and the water, the underground water came on the surface, because this is Bhabbar zone. Bhabbar zone from groundwater point of view is called very shallow groundwater conditions. So, the groundwater conditions are shallow when stresses were built up, and the water which had the higher temperature relatively than the ground temperature came near to the surface, and which has brought this thermal line, and that too along Himalayan frontal thrust. So, in both cases, in case of Chamoli as well as in case of this Nepal earthquake, the thermal anomaly appeared, and of course later on they disappeared. Though typical pre-earthquake thermal anomaly or anomalous regions which we have seen in case of Bam earthquake and Jarand earthquake of Iran, which we did not observe in these two Himalayan earthquakes of Chamoli and Nepal earthquake. However, definitely in these two earthquakes we have observed clear appearance of a linear thermal anomaly, and about 60, 70, 80 kilometers south of epicentral region. And the reason I have just explained, because of shallow groundwater conditions and because of this earthquake and shaking, the water which has relatively higher temperature compared to the ground temperature, it appeared and it created the thermal anomaly. So, analyzing remote sensing data, especially the thermal remote sensing data, thermal channels data of these 28, 29 earthquakes of different parts of the world, what we have observed that thermal anomaly above earthquake having magnitude 6 and above, if we are getting completely cloud free images, then thermal anomaly is being observed. In almost in all these cases we have observed. There might be some offset which I have just explained, but thermal anomaly have been observed. However, if earthquake is say 4 magnitude or 5 magnitude, then this is not bringing this kind of energy or temperature changes, and therefore we could not detect any such thermal anomaly in earthquakes which are below 6 magnitude. Earthquakes, whether if they are occurring in thrust fault regime or in other fault regime like normal fault or others, they both are showing this anomalous region. But especially in the Himalayan region, what we have seen the examples of thrust fault regimes of Chamoli earthquake and Nepal earthquake. So, likewise we have analyzed again, as I mentioned, about 28 earthquakes. This is a sort of summary here. The important point note to here is 0000 column shows the day when earthquake has occurred, and these are on you can say the y axis on this table. You are seeing different earthquakes which has occurred. They are given in very abbreviated forms and details are in the bottom. And so, like the Bhuj earthquake, in case of Bhuj earthquake, the anomaly was observed 3 days before. In case of the Sumatra earthquake or Jarand earthquake, the anomaly was observed 1 day before. So, likewise what you are observing here, that on the left side how depending on the data set, if data is weekly data set, then it is a different scenario. But if it is a daily data set, then it is a we are getting anomaly which are 3 days, 4 days before an earthquake event. Again in daytime data, the anomaly is seen quite close to the day of earthquake or earthquake event, but in nighttime data, as in you have seen in case of Bam, it has been noticed 5 days before. So, likewise the analysis have been performed. Some understanding about this pre-earthquake thermal anomaly from different earthquakes of different parts of the world has been developed, but still lot of work is required to be done before we reach to that milestone when we start using this one as a reliable earthquake precursor. Among one of the precursors, among many precursors are there, like foreshocks they are there are changes in the radon gas emission, there are changes in water level conditions, and there are other perturbances which occurs or just before the earthquake. So, this is one of the we can consider as one of the earthquake precursors which is occurring before an earthquake if magnitude is 6 and above. So, some earthquakes, very carefully chosen words to summarize all this what we have discussed in this discussion is that some earthquakes, not all, may be preceded by detectable thermal anomaly. Many examples I have shown of to you from different parts of the world. 28 recent past earthquake showed transient thermal anomalies before the events. Of course, this analysis is all after the earthquake has occurred. So, it is a hindsight postmortem analysis. Thermal anomalies for earthquake with large magnitudes have a larger spatial extent. This is very obvious. If earthquake is large, higher magnitude will have a large anomalous region, and if earthquake is quite shallow, it will have a smaller anomaly, but intense anomaly. So, that is also observed. And rise is temperature, LST, that is land surface temperature, detected or recorded by these thermal channels ranges between 5 to 11 degrees centigrade above normal. And duration of pre-earthquake thermal anomalies was done or more in case of earthquakes of larger magnitude, that means before the earthquake, few days before the anomaly is seen, but in case of relatively smaller earthquake this cannot be. In that case the short time difference is there. Further in discussion, maximum buildup of thermal anomalies at night time, as you can see compared to daytime in case of BAM earthquake, and location of thermal anomaly epicenter offset is the result of active fault characteristics. I have shown you the 3 examples, one from Barmedis Algeria earthquake where offset was there, in case of Chamoli earthquake, and of course in Nepal earthquakes of 2015. Pre-earthquake thermal anomaly depends on earthquake magnitude, terrain and meteorological conditions. If the drawback of this technique or the big limitation of this technique is we need to have a completely cloud free time series data. So, we do not have control over meteorological condition, but if an area which is having a complete cloud free data, then our interpretation analysis becomes highly reliable and level of confidence would be very high. But if we are having intermittent cloud cover, then our level of confidence in the analysis goes really low. Now, some more these remote sensing applications we have seen, but very quickly I will go that we employed this SAR interferometry technique in the earthquake of 26 January 2001. And the important point here, it is not these are the image or interferogram which I am showing here are not co-seismic. This is the post seismic. And what we have observed in case of this 2001 earthquake, that even in between 2004 and 5, as you can see here, after 3 years or 4 years of earthquake event, ground deformations were still going on, and we could detect and record, estimate what kind of ground deformation. So, if I blow up, as you can see in the Kunji SAR area, you are seeing these fringes very clearly. And one more image which you will see here, that what you can observe here, that the subsidence of about 17 centimeter has been observed in Kunji SAR area, and that too after roughly 4 or 5 years after the earthquake event. So, this is the first time the SAR interferometry technique has been employed to even estimate ground deformations post seismic, not co-seismic ground deformation, but post seismic deformations even after 3-4 years later. So, this technique, if satellite data, such data is available now, like currently from Sentinel, we know where earthquakes occurs, and say if I take the example of India, then we know which are the seismically active regions, highly seismically active regions like zone 5 in seismic zoning map of India. Data is available on regular basis. So, if we keep analyzing the data and we find some ground deformations like here these are of course post ground deformation, then probably we can also detect pre-seismic ground deformations employing SAR interferometry technique. Because now it is possible, because sentinel data is available free of cost on net, and only regular analysis of those areas which are seismically active regions of the country, if they are observed, monitored regularly, analyzed, data is analyzed regularly, we can even detect pre-seismic ground deformations if there are any. So, with these words I thank you once again for this two parts discussion on how remote sensing images, data sets, whether it is a visible, whether it is a infrared and thermal and SAR interferometry, that is radar or microwave data, can be employed in earthquake related studies. As said in the beginning of this course or also in between several times, that remote sensing technique is generic technique. I showed the examples in this last two lectures. I have shown the examples of how these techniques or remote sensing technique can be employed in earthquake related studies. But one can use the remote sensing data for water resources or for flood studies or for drought monitoring, for agriculture. So, there are various applications are being developed, have already been developed or can be developed. One of the examples, as I have said, to detect pre-earthquake ground deformations if there are any. So, with this, this brings to the end of our discussion. Thank you very much.